Next, we discuss a very important concept that is a decibel. We know that the impedance, branch variable, and the network function of a circuit can all be complex numbers. Their module and phase angle can all be function of angular frequency. We illustrated it by taking the network function as an example. Sometimes the module of the network function can be 10 to the minus 4 to 10 to the 3, which involves 7 orders of magnitude. The frequency we care about might be 1 millihertz to 1 gigahertz, which involves 12 orders of magnitude. In this case, if we qualitatively draw the transfer function, because the range of the horizontal axis and the vertical axis are very large, so it is possible to hide the trend. So what can we do? As you have expected, we might as well use a way of a logarithm. That is to say, the logarithm of the module changes from minus 4 to 3, which involves 7 numbers. For frequency, if we solve its logarithm, then the whole range is minus 3 to positive 9. By logarithm, a nonlinear transformation, the chain of the transfer function becomes very clear and visible. The study of the transfer function started from the acoustic field. People often hard to determine the intensity of a voice. So naturally, the size of the voice is determined by the ratio of the voice to another reference voice. The range of the ratio could be very large. So Bell presented such a solution first. That is, eta equals log A over B. We found later that the value is still too small. So further put forward the concept of dB, decibel. The value multiplied by 10 or 20. The relationship between dB and Bell is a bit like the relationship between decimeter and meter. Why did it multiply by 10 or 20? It was multiplied by 10 at the very beginning when people studied the proportion of sound. Then we expanded the search range from voice to the electric field. The strength of the voice is proportional to the power. That is to say, it is natural that dB equals 10 times log P2 over P1. We also know that the power is proportional to the square of the voltage, so it becomes 20 times log U2 over U1 after picking out the square item. Thus, we have two kinds of definition about dB. One is 10 times log P2 over P time. Another is 20 times log U2 over U1. About the benefits of introducing logarithm for nonlinear coordinate transformation, we might as well see a simulation. In this simulated circuit, we introduce a new instrument that is a Bode plotter. We will discuss in detail about in the introduction of simulation 6. We only need to know that the input of the Bode plotter is the excitation of the system and the output is the response. The instrument can easily draw the AF and the PF, which are the module and phase angle of the transfer function. You can see that the input connects to the voltage of the source and the output connects to the capacitor's voltage. We run the circuit and stop it. Now we look at the amplitude. If the horizontal axis and vertical axis are linear coordinates, the horizontal axis is from 1 Hz to 1 MHz, vertical axis is 0 to 1, there's almost no waveform of AF characteristic. We drag the cursor, the value is 999 milli when 1 Hz, and it's decreasing with the increase of the frequency. The waveform is obviously too troublesome to observe. We might as well express the horizontal axis in logarithm coordinates. The vertical axis is also expressed by logarithm coordinates. Although all the numbers have not been changed, but after log nonlinear transformation of coordinate system, we can find that AF characteristic of the transfer function shows very clear properties. The value is high when the frequency is low, and it gradually decreases with the increase of frequency. Well, this is the end of this lecture.